Welcome to this very special session of Shadow the Scientist. My name is Jamika Marshall, and I am the Shadow the Scientist Programs Manager. Yes, so someone has requested captions for this meeting. I'm enabling closed captions in English. If you need it in a different language, of course, please feel free to send me that request, no problem. Thank you. Okay. Now, Shadow the Scientist is an initiative that's brought to you by an amazing team of individuals at the University of California at Santa Cruz. So if you're just joining me, let me go back a slide. If you're just joining, again, my name is Jamika Marshall. I'm the Shadow the Scientist Programs Manager. Shadow the Scientist is an initiative brought to you by a team at the University of California at Santa Cruz. And as you can see, I'm here at the Hilo Base Facility for Gemini Observatory North. The control room is right behind me. Now, for those of you who are not familiar with Gemini, the International Gemini Observatory actually consists of two. It's twin 8.1 meter optical infrared telescopes that are located on some of the best locations in the world. As we're in Hawaii, the Gemini North facility is located atop Hawaii's Maunakea and is part of an international community of observatories. Now, by incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini Partnership explore the universe in unprecedented depth and detail. Now, as I was saying, our observations this evening will be taking place right behind me in the control room. And there we will actually be shadowing Mateus Rodriguez and Charlie Figura. Before we get to Mateus and Charlie, let me introduce you to your science hosts for this session. We have Brian Lameau and Eunchung Kim. Eunchung, Brian, welcome to this session of Shadow the Scientist.
Hi, Jamika. Thank you for the great introduction, as always. So hello again, everybody. It's been a long time no see. We are here now. I've switched backdrops, so just moved to a different part of the base facility, the Gemini base facility. And I have Eunchong here on my right, who I don't know if you actually officially introduced yourself on the call earlier today. So maybe I don't even know if I go. Okay, so I'm going to officially introduce myself, and then I'll pass to you to officially introduce yourself, and then maybe we can pass to the control room to officially introduce themselves.
That sounds good.
So in case I didn't mention it earlier, my name is Brian Lameau. I'm a staff scientist at Gemini North Observatory. So I'm based in Hilo, Hawaii, on the Big Island of Hawaii. I work here in support of observations. So when people apply for the observations on the telescope, I help to get the instruments ready. I help to get the observations ready. And then on occasion, I take observations at nighttime. I also plan the queue during the day and do other associated activities. I'm also a researcher, so I work on high redshift galaxy evolution, specifically on galaxy evolution as a function of environment. So I'm really interested in clusters and protoclusters of galaxies from redshifts 0.5 to all the way to infinity. And so I do a lot of, it's mostly from observational perspective, although I dabble in simulations as well. I do a lot of observations on large telescopes, including James Webb, Hubble Space Telescope, Gemini, both Geminis, Keck and Subaru. So Eunchung, that's to you.
Hi everyone, I'm glad to see you here because when I was graduate school student, so I have attended the summer school several times, and now I am here as a mentor or something like it. So yeah, Actually, I was in the KASI as a member of Korean Gemini office. And also, I am in here as a Gemini Science Fellow. And it's been only 1 year. Yeah, the next month is 1 year.
Yay.
Yay. So, yeah, I usually my research field is related with the circumgalactic medium in the high redshift and also the proto-galaxy cluster, just like Brian.
Oh.
Okay, I hope you have a great time in this session. Thank you.
So, Matty, Charlie, if you have a second, I'm not sure if you're acquiring right now, but if you have a second, would you mind introducing yourself and your roles tonight?
Hi, everyone. Can you hear me?
We can hear you
Yeah.
loud and clear.
It's a pleasure to be with you all this night. I'm here with Charlie. We just moved the telescope, so Charlie's a little bit busy. We are science operation specialists here at the Gemini Observatory. Right now, I'm the observer in this room. I will be taking data and doing quality assessments during the whole night, while my friend Charlie will be operating the telescope and taking care of the instruments and the telescope itself, all the infrastructure and the safety for the whole night. So thank you for joining us.
Brilliant, Mateus. Thank you so much.
Just to set the stage here, so we are now about
Mateen, we are guiding
40
at 200 hertz.
45 minutes to an hour after sunset. So Matty and Charlie have calibrated the telescope for the evening, so have gotten the optics ready for tonight's observing. They took some calibration observations, including a sky observation a bit earlier. And so we're just entering now into, I think, roughly 12-degree twilight. So this is right when science time starts for a lot of observatories. This is when the sun is 12 degrees below the horizon. And so the sky is dark enough, especially in the infrared, for us to be able to observe without too much interference from the sky. So I think what was the first observation tonight is a GMOS observation. And so as I mentioned in today's workshop earlier, GMOS is one of the most used instruments on both Gemini telescopes. And it is a relatively dark sky right now. I'm not sure what the actual moon phase is, but it's probably approaching first quarter. But so we're in relatively dark time right now. And so that's a really good
39%
time.
illumination.
What's
It's not
that,
that dark, Brian.
39%. Okay. All right.
39%. It's kind of bright.
So we're right now, let's see. Yeah, we're at about median brightness right now. It's actually going to get a little bit darker. So we're in like just before first quarter. So sky, yes, the moon's out in early evening, and then the sky is going to be very dark after that. So we're taking observations of a reasonably bright target right now. And then we'll move on in a little bit actually to the interstellar visitor that we talked about earlier today. So 3i Atlas is going to be observed a little bit later, we hope. Okay, so let me orient a bit more. Okay, so here we are on the big island of Hawaii. This is Hilo down here. This is the Bay of Hilo right here. So our base facility is located just about at sea level, about 100 meters above sea level in the town of Hilo. We're observing from Maunakea with a fiber optic connection to Maunakea. This is the current picture of Maunakea right now. So this mountain has 10 active telescopes right now, two radio telescopes, and then a suite of optical and near infrared telescopes. I hope I'm not saying anything silly. but close to those numbers. And so some of the telescopes you may have heard of before are the Keck telescopes, two Keck telescopes. Those are on the northern plateau of Mauna Kea. In fact, if we look at our north cam, we can see one of the two Keck telescopes right here against the silhouette of as a silhouette against the backdrop of the sunset. The NASA Infrared Telescope Facility is one you may have heard of. And the Subaru telescope is another one that you may have heard of. This is just sitting over to the left in this picture right here. You can't see it, it's off screen. And Gemini is on the eastern ridge. Actually, I can bring up, so. So Gemini is here over on the eastern ridge of Mauna Kea. So this is the topographical map of Mauna Kea. The Subaru telescope, the two Keck telescopes, the NASA Infrared Telescope Facility, the Canada-France-Hawaii telescope, the University of Hawaii 2.2 meter telescope, which was, these two telescopes were instrumental in discovering and first characterizing 3I Atlas. So Mauna Kea has been very involved in the discovery and the characterization of this object. And the United Kingdom Infrared Telescope Facility, which is now run by the University of Hawaii. And so it's at about 4,300 meters that we're observing, but there's actually nobody up there currently. So we're observing from the base facility. The telescope does not have anybody inside. There are some telescopes on Mauna Kea where people go inside and they observe from the summit. Subaru is kind of a hybrid model where there's people up at the summit and there's people down in Hilo. They're actually right next door to us. Keck is also a hybrid model where there's people up at the summit and down here. IRTF is almost exclusively from the summit, but we transitioned to base facility observing about 6 years ago. And so this is much more comfortable for us. We're not up on Mauna Kea, which is very beautiful, but we're here at 100 meters where we have things like, I don't know, coffee and I don't know, easy to access places to eat and things like that. So it makes observing life a little bit easier because it is, the best observing sites in the world are not entirely hospitable to human beings. So, right, so let's go to this here. So this is just to give you all an idea of what the conditions are right now. So of course, when we observe from the base facility, there's nobody actively on the summit. And so we need a lot of cameras. We need a lot of information to be able to understand what the conditions are in the telescope dome, on the telescope, within our instruments, on the summit, surrounding the summit. And so these cameras that we just looked at earlier, these are access cameras that we have that are on the side of our dome. This allows us to see, for example, if there's fog rising on the eastern part of the slope of Mauna Kea. This is, so Charlie's job tonight as operator, so we have two roles at nighttime. Charlie's job as operator is they will make sure that the telescope is well protected. So that's their main job. To make sure that everything is safe, that we can use the telescope for years and years and years to come. So if there's any danger, they will immediately close the dome. If humidity rises, if we have active volcanoes here, so if humidity rises and there's a volcano outburst, that can be very bad for the optics. So they will close the dome very quickly. If we have issues with the telescope at night or some of the instruments, or we have some ambiguity, some uncertainty about what exactly is going up on at the summit, they are the point of contact for everybody at the observatory, because we have about 80 people, 80 staff members working here during the day and some at night to make sure that everything is ready during the day as best as they can. And then if something comes up at nighttime, that they can assist with keeping the observations going. So these cameras are very important for us to be able to understand the conditions. We have satellites, we have cloud thickness monitors. And so we can not only see the conditions currently, but we can predict the conditions that are coming in. And so that to some degree of certainty. And so that's Mateus's job this evening is to, we talked earlier today about a Q coordinator. So a lot of telescopes work on a Q system right now. So we have this big pool of observations for a given semester, thousands of observations that we could potentially take on a given night for a given set of conditions. And so we have the Q coordinator during the day that constructs something like 10 to 15 different plans. And these plans are some combination of weather conditions. And so when we talk to you guys about, we'll go into this a bit more in depth later, but when we talk to you about the interrelationship between what you propose for and the weather conditions that you request, this really comes into play, because you can imagine that a bright source, maybe a spectroscopic source, you wouldn't necessarily need the best image quality, the best cloud conditions that Maunakea has to offer, but rather you could take somewhat degraded conditions. And this is where like poor weather programs come in. But if you are looking for very faint galaxies or very faint objects very far away, or they're small, then you perhaps need something very good conditions. And so the Q coordinator comes up with a set of plans that says, okay, these observations are best for these conditions. And this is based off of the proposer's idea of what the conditions should be. And this is based on integration time calculators, like the examples that I showed you guys earlier today. And so Matty's job is one of his many jobs tonight is to assess the conditions. So he's made a measurement. Let's see, shows up here. No, not yet. But so he's made a measurement earlier in the evening of the image quality for this evening. And he's estimated, so we break it up just to make it easy on ourselves. We break it up into these percentiles. And so lower on this graph is better. So you can see that, so this is 20th percentile best here, if you can see my cursor. And so better than 0.6 arc second seeing at 500 or 5,000 angstroms. That's Maunakea provides that, or it's through Gemini's optics, but Maunakea provides that 20% of the time. And then better than 0.85 or 0.83, that's IQ 70, what we call IQ 70. So 70% of the time, it's better than that. And this is basically the visible. So this is what we see as visible. This is like the peak of the sun spectrum. So 70% of the time in Maunakea, you're getting better than let's say 0.8 arc second seeing. And then, so tonight, it looks like it's right in between IQ 70 and IQ 85. So we're roughly at about 0.85. And we can see this a bit better if I go to this screen here. So this is an active measurement of what Matty is seeing. And actually, Charlie wrote this software here. And what they did is they took engineering data that we have. So we are constantly outputting information from sensors. This could be temperature sensors. This could be measurement sensors. The sensors on our primary mirror, sensors on our secondary mirror, sensors on wavefront sensors. So sensors on top of sensors. And right here, this graph right here, Charlie has ingested the information that's coming out of these sensors. In this particular case, it's our on-instrument wavefront sensor for GMOS. So GMOS is measuring a bright star. It's passing this the light of that bright star through what's called a Shack-Hartman array, and it's measuring. It's guiding. First of all, so it guides so that it makes fine adjustments to the telescope and to the secondary mirror as the conditions change and as our tracking gets a little bit off. But it's also measuring the full width half max. And so Charlie has plotted here a corrected value, because we have to air mass correct this, and there's a couple other corrections that are involved. So that's the final value should be the darker green line. Not sure what air mass we're at right now, but so we're actually kind of dancing around IQ 85, IQ 70. Right now, at this exact moment, we're measuring about halfway in between IQ 70 and IQ 20. So so Matty would at that point would say, okay, so the seeing is roughly average or a little bit worse than average. The cloud cover based off of maybe this plot here. This is not the one that we use all the time, but this plot here. This is a measurement from the Canada, France, Hawaii telescope, which is right next door. This is a measurement from where they're pointing, and this is an average of a bunch of different stars on a kind of sidekick telescope that they have that points where the telescope points. And their measurement is that there is 0.06 magnitudes of attenuation. And this is what's called CC70. So 0.06 magnitudes of attenuation is not much. In flux density, that's like less than probably 2%. So it's a really small amount of attenuation. But Maunakea is so amazing that 50% of the time or better, we have photometric conditions in that there is not a single cloud in the sky. And so we're able to measure with zero attenuation. So this is actually considered below average in terms of cloud cover. So Matty would take that information. If we have water vapor sensors from the two radio telescopes here. And so if that were important, water vapor is actually not important for the optical, but for the infrared, it can be very, very important. And then also, Charlie corrected me earlier about this, the surface brightness. So currently, the surface brightness is in about the 50th percentile, so it's about median. But of course, this depends on a variety of different aspects of the night sky. So are you near 12 degree? Because then, of course, as the sun gets further and further below the horizon, it gets darker and darker. Is the moon out? What is the phase of the moon? And so currently we're sitting at about 50%, 50 percentile in terms of surface brightness. But it's going to get darker as time goes by. So Matty ingests all that information and he decides, okay, we're in this plan. And then he grabs the various observations that are associated with that particular science program. And then he asks Charlie to move the telescope there. And Charlie says, yes, okay, that sounds good. Or nope, I got to close, there's humidity. And if he says, yes, that's good, then Matty, as soon as Charlie says, we're good, we're there, Matty starts to set up the observation. And so, Matty, are you actively taking data? Like, can I bring SegPlot up?
Yes, I just took a Kali radar, a spectrophotometric star, and we are moving to our first real target of the night, which is gonna be a star, I think. Not sure.
Galax.
Perfect. Okay, awesome. So this already shows like this is already really cool. So beautiful. Anytime you take an observation from the ground, from space, anywhere, you have to calibrate it. Optics are imperfect. People are imperfect. So setting up the observations, acquiring the observations, telescope's imperfect itself. So the movement, maybe we don't track like perfectly over time. There's detector noise. The detector has a certain level of inefficiency. There's an atmosphere. So atmosphere attenuates photons. It emits other photons that you don't want. The detector is imperfect with respect to, so if you put a uniform illumination source, it's not going to be uniformly illuminated on the detector. And so all of these things have to be removed because you're required to get to the essence of the astronomical object that you're looking at. You want luminosity, you don't want flux density. So you want the actual intrinsic information about the source. And so this is what a lot of the early part of our night is spent doing. And any, if you do classical observing, you would usually do this yourself and you would set up these calibrations yourself. Gemini as a service provides all these calibrations. So this is actually taken out of the partner time for each one of the partner countries. And so we have a big pool of time in which these calibrations are taken. They're usually taken early in the evening so that we don't waste really dark sky, or we better utilize really dark sky to take science observations. And so what you're seeing here is a GMOS long slit observation. This is not the full array, so I think this is just a central, maybe sixth of the array. There's actually 3 arrays here, but in the Y direction, it's only about a sixth of the array. And so this program was also written by Charlie, so it's a super helpful program at nighttime. One of Matty's other jobs is to quality assess the data. So this is really important because if we, for example, we acquire on a target and we think we're on the target, and then we take the observation and you don't see what you expect to see, like this is a very bright star. If you see a very faint star, you might say, maybe I'm on the wrong star. And so then you have to go back and check the finder chart and, okay, maybe I pointed wrong. You check the right ascension, declination, everything. But here it looks like we're on a nice and bright star, and you want a nice bright star that has a known spectral type so that you can response correct your data. So basically you're response correcting for losses due to the slit, losses due to the quantum efficiency of the detector, losses due to the optics, so on and so forth. So I'm just going to make a cut here. Okay, so all right. So this is what the spectrum looks like over here. There's a little bit of, let me see if I can zoom in a bit. There's some weird noise in there, which I'm not sure what exactly that is. But ooh, it's very laggy. Sorry, it's pretty laggy. This is the VNC connection. Okay, so that's it. So that's just one detector there. So these gaps right here are actually gaps in between the detectors. So one of the things that you might be encouraged to do when you're thinking about submitting a telescope proposal, the science ideas are great, but to realize them, you need to have really good setups for your calibrations. So you're only as good as the observations that you take. If you can't fully realize them, then in the end, then you can't do the science. And so these detector gaps are, so wavelength goes from let's see, so blue is on the right and red is on the left. And so these detector gaps actually induce they remove a small chunk of wavelength. And so you actually, in order to get the entire spectrum, we don't do that in this case because it's not necessary, because it's a calibrator and we can kind of interpolate over it. But if you wanted to get all of the full spectrum of your source, you would shift the grating inside. So there's a grating that's dispersing the light. You would shift it just a little bit so that the light that was removed, or that was not hitting the detector at this location, in this observation, would move over to the detector portion. So they would be incident with the detector. And so then you get one observation at one central wavelength, another observation at a different central wavelength, and you're able to reconstruct the entire spectrum. Another thing that you might do is do a spatial dither. So the spatial axis is like this. So we have a slit, right? It's usually a 1 arcsecond slit. And so moving along the slit is in this direction. And so you would do that because potentially, like, so for example, you see here, you have cosmic rays that hit the detector. And so you can get rid of those with multiple exposures. Usually 3 or 4 exposures is good enough. But this is a defect, right? This is not part of this is not part of the sky. This is not part of your astronomical source. This is part of, this is something coming in from the atmosphere that's, well, from the cosmos that's then hitting the detector. And in fact, this detector, for all its virtues, it's very sensitive in the red, blue, and green, but it collects a lot of cosmic rays. And so you can see as I just scroll along, a lot of these little streaks. But also there are defects on the detector, and they're not actually, the GMOS detectors are really clean compared to some other detectors I've seen, but there can be like bad columns or bad rows. And so if your spectrum just happens to land on a bad column or bad row, moving the telescope up and down, so the source apparently moves up and down on the detector, then you can stack them all together, and then you can median combine them or variance weight them or whatever, and you can create a spectrum that removes all of these artifacts. So yeah, these are some like of the types of things that would generally be done with observations here, because the source is so bright. We can interpolate over these detector defects, especially since the exposure time is very, very short given the brightness of the source. But what we do next is we go to a calibration frame. So not only do we take the response from this source, but if we were to just take it straight up without making any correction for the optics or for the atmosphere of the detector, we would not get the right answer. And so we actually have to calibrate the calibrator. And so this is a flat field observation. And so if so this is the response of the GMOS CCDs. These are just counts versus wavelength, let's say. And you can see as I move this around, this is not a flat response. So there is some illumination pattern here, and that has to be removed in order to get a proper response from the astronomical object. So all of this is in fact set up. So when you make, and this is true of any observatory that you apply to. So in the future for GMT, there'll be staff scientists for GMT that will help set up the observations. And so this is not something you have to do on your own. Even in classical observing, it's very common for you to go meet with a support astronomer before the night. They will walk you through you'll do afternoon calibrations. They'll walk you through the process. They'll suggest certain tricks for you. They'll suggest some tricks at nighttime. And for us here at Gemini, we actually do this comfortably during the day, where you would email us and you would say, hey, I'm thinking about, I'm setting up this observation. I've done this and this and this. What do you think? And we have enough time to go back and forth over email many, many times. And Songchul does this quite a bit too, with lots of programs. And we set it up so that everything is absolutely optimal at nighttime. So we already have all of the calibrations set up. We already have all of the plans set up. As instrument scientists or instrument teams, and Chung is on several instrument teams, we make sure the instrument is extremely well calibrated. So when you request a central wavelength and you request to go to this particular configuration, that there's no problems with that, or we hope there's no problems with that. I'll go to, oh, okay. So actually something is happening right now. Figured to see an IST.
Okay, in the meantime, can I answer the second question?
Yeah.
Yes,
In
please.
the chat? Yeah. What happened to the queue when satellite intervened the image? So yeah, when I was in the observing shifts, I've seen several times the satellite passes the image, and if the satellite pattern is not overlapped with the really important science target, then we just want to let the PI knows and ask them, do you want to take again? So if PI wants to take again, then usually we retake that image. But if PI said, I don't think we need to take again, then we just set them as a pass.
Yeah, so I mean, in lots of cases, it's an imaging observation, right? And it's usually that they're taking dithers of multiple positions on the sky. And so let's say you have 30 observations across a certain patch of the sky. If one observation has a satellite trail that goes through it, you're usually median stacking or you're somehow clipping out artifacts because satellites aren't the only thing that happen. Like, for example, the cosmic rays are an issue with the detector, and that could very easily hit the science target. But you're stacking all these, you're shifting and stacking all of these things together. And so in the end, if one observation out of 30 isn't good, your signal to noise that you recover is basically the same as if you clip that observation out, is basically the same as if that satellite weren't there. But if it's one spectroscopic observation and it just so happens to illuminate the slit, I mean, we have the observation open for faint objects for 20 minutes at a time. And so if a satellite were like, we got really unlucky and it happened to pass right in front, we would have to probably retake that whole entire observation.
Yeah, so shorter exposure time program, it is easily can take again, but if the long exposure time, like one image per maybe 20 minutes, 30 minutes, that could be really makes upset all of me. Yes.
But it's not very common that we have that kind of issue. It's usually a single frame, and maybe it's a couple minutes that we lose. And in the end, it's not too damaging to science. It will. There's very subtle effects that. So, like for example, for the Rubin telescope that just came online in Chile, it can cause all sorts of issues because they're trying to do very precise measurements, like weak lensing tomography. So. The flux of these satellites can splay out and really cause issues for measuring very fine details of shapes of background galaxies. Can actually impose itself in the mass reconstruction maps that they're attempting to create. So they have a whole team of people that are looking specifically at the effects of satellites on their data. So it really depends on your scientific purpose. It could be that it doesn't do anything, and it could be that it does a whole lot. So that's probably the answer to like most things, honestly. It's, can your science handle it or not? And usually, as we're pushing to bigger and bigger telescopes and tougher science cases, these little, what we call systematics, so these little tiny things in the data, they end up mattering quite a bit. And so you should think about this when you're making your science cases. You would like to make your observations robust to systematics that exist in reality. And so if you're looking for example, spectrophotometric precision of 0.1%, I'm sorry to say, you're probably not going to get it. You can pretend, we can say that we got it and we can think that we got it, but in reality, it's probably not that good. And so, you want to make sure that, if like 5% spectrophotometric precision, that's totally reasonable. It's hard, but it's totally reasonable. And so, making sure that your science case can handle that is really important. So one of the things I wanted to mention, I think that Matti is taking some science observations now. This here is the GMOS. So we're taking GMOS observation, long slit observation, as we mentioned earlier. This is the optical path of GMOS. It's just a display. This is an instrument status display. And so this is the all of the optical elements that are sitting within the GMOS instrument. And so this is the on-instrument wavefront sensor that we talked about earlier. We have a mask, a filter, two filters. So this mask is just a 1 arcsecond slit in this case. We have a grating, and then the shutter is closed right now, so Matti is not taking data at the moment. But if you were to open the shutter, so if you were to expose, then it would expose the light to the detector. And so this is the job of the instrument scientists generally during the day, and the SOS is the science operations specialists, which the role of Matti and Charlie. They spend a lot of time during the day making sure that our instruments are like absolutely in top shape, ready to go, that all the different instruments are working well to a precision of a very, very high level of precision, so that when we get there at nighttime, there's no problem. And so, yeah. So, Matti, if you're not busy, maybe you are. Are you acquiring on the source?
Not really. So we are waiting for the sky brightness to get in constraints. It's still too bright, and this program requires dark skies. So we are about to start this observation. It's
Okay.
about some cataclysms, variable stars.
Okay, nice. Okay, so you've already acquired on the source, and you're literally just waiting to press the expose button.
Exactly. So I'm gonna press it right now. And there we go.
They should have had a sound effect ready to play.
Yes,
The alert
we are
sound.
about to start science, and there we go. GMOS is
For science of the night.
for science of the night.
Sweet. Okay, that's always a good feeling. So Matti and Charlie are so awesome. They were ahead of schedule. They beat the
It's true, we are.
yeah, humble brag. So this is the source that Matti has zoomed in on. It was that this was an image of the source, and they placed the slit just over the source. So the light is coming in through the slit from the source only at that location, and then it will be dispersed, and they'll get a spectrum of that source. So probably it's like yeah, there we go. So this is just again about the central sixth of the detector of the 3 detectors, and that's the source right there. And Matti and Charlie lined it up. So usually we're off by sub-arc second precision on the pointing. This is an illumination just of the slit, so against the sky, so there's no source in that. And then all of a sudden, so it was the telescope was moved such that the slit fell right into the source fell right into the slit. That looks pretty dang well centered. And the seeing actually looks pretty decent as well. And so that is what we need. And so then we're only getting the light from that source, and it's being dispersed out. So there was a question from Sangchul about global climate changes over the years, and if we've noticed any changes in the observing conditions on Mauna Kea. So I've been observing on Mauna Kea actually for more than half of my life, but it's very hard to get time on a telescope. So my sampling has actually been only consistent over the last 4 years that I've been at Gemini. Otherwise, I'm on the telescope maybe twice per semester if I'm lucky, doing my own research. So I might pass that. I know Charlie's had a lot more experience on Mauna Kea than I have, and I could say some anecdotal things, but maybe Charlie could speak to any trends that they've seen over the last however long they've been working.
I think a lot of I'm not sure that I don't have anything more than anecdotal either. A lot of my I've been here at Gemini for, I guess, 5 years now, something like that. And prior to that, I was doing my observations, studying massive star formation using submillimeter telescopes, so J-CMT, primarily here. So the sky constraints are considerably different in submillimeter. So I haven't really noticed anything, and I haven't seen any data that have looked at trends over the past couple decades.
Yeah,
So I'm not
I
going to be helpful on that front.
Okay. All right. Well, yeah, I mean, I would say it's been remarkably consistent, at least in my estimation,
Mhm.
over the time I've been observing here. Um, the lows seem more low and more persistent. The highs seem more high and more persistent. So when we're clear, it seems like we've been clear for longer periods of time, and when there's bad weather, it seems like there's been bad weather for longer periods of time, relative to what I remember when I was younger. But yeah, I'm not sure. It's still an amazing observing site, although I'm guessing global climate change is not gonna help over the long run.
I will note that I don't think we have updated our limiting threshold values for IQ or image, for image quality or cloud cover or water vapor in maybe ever. And I don't think that the values that we see over the course of the year are substantially different from what those thresholds indicate. So our
Agreed.
IQ20 says that we have conditions this good or better 20% of the year. And I think that's probably fair, that comes down to anecdotal evidence, but it seems to be fairly consistent
Yep.
or
Yeah.
close enough that it doesn't matter.
And it's checked. So we do check the statistics, and the statistics seem to more or less comport with the values that we have now, and that's at both observing sites. So that's not just Maunakea, that's Cervicon as well. So Gemini South as well. Yeah, so the number of nights lost to weather has been reasonably consistent over the years, I would say. Now, this is averaged over a year-long temporal baseline. So, if you're going for a classical observation, that's one night out of the year. And so, you can get very unlucky, and that's small number statistics. And so you can get this idea that, things are very, very bad on Mauna Kea. And that's why my experience of Mauna Kea for a long time was just getting a one night here and there. And so I would have years where I would not get any good data, just because it so happened that I got bad nights. But when you average that out over the course of the year, yes, it's been roughly the same. Okay, and then there was another question about detector gaps introduced in the first place. Is it a technological limit? This is true of any, effectively any instrument. There's always going to be detector gaps, and I'm not well versed enough in the technology to understand why those gaps have to exist. But this seems to be some limitation of seeding, and I'm guessing you have to read these detectors, and so there's amplifiers associated with the detectors. There's electronics around that you also don't want the detectors to interfere with one another, so you have to minimize electronic noise. And so having a gap in between the two detectors is a very sensible thing to do, just from a electrical engineering perspective. So now you can make these detectors bigger, but then of course it becomes very expensive. Wow, what's that?
Brian, you also run into to noise, to readout time considerations when you make a big monolithic detector that scales non-linearly.
Yeah. Right. Yeah. So I think there's advantages and disadvantages to a variety of different designs. And so again, it depends on what you're what your goals are, what your science is, and what's important to you. So we can easily get around these detector gaps. It's not really a difficult constraint for us. You just dither on this. If you're taking imaging, you just move the telescope around a little bit and dither. If you are taking spectroscopy, you move along the major axis of the slit, and you also shift the grading a little bit. So in the end, it's you're going to be taking multiple observations anyways. You're going to design your program like that you would do that whether there were detector gaps or not, and so you can easily get around it. It's not any added overhead or anything like that. So yeah, I guess Matthew just took a science spectrum, and now he's taking it flat. And I'm guessing he's going to take an arc right afterwards. So we'll take we're pointed towards our Gemini calibration environment. Let's see, looks like it's just piping out an image. Yep, okay. So this is, wow, it looks like there's some reflected light in
Yes.
decal. Yeah, that's a funny illumination pattern. Wonder if it's just a stretch. But anyways, this is a elemental lamp that's sitting in our calibration environment. So we take this simultaneously, sequentially with the science observations. And so this is taken when the telescope is pointed at the same location on the sky, and all of our instruments are sitting down in our instrument support structure, our Cassegrain focus, down at the bottom of the telescope. And so it's rotating around as the sky is rotating and as the telescope is moving. And so all of these introduce gravitational flexure into the observations, and so arc lines move around. The source can move around, and so we want to take observations to calibrate the wavelength as a function of detector position at every point that we're taking scientific observations. Okay, and Sean, can I pass over to you to talk a little bit more about the contact scientist role and the Q coordinator and what is done during daytime work? I can stop my sharing for a sec.
I can share the screen. Okay, can you see my screen? Yeah, maybe I can briefly introduce the QC's job. So I'm gonna take the QC part because I was the Q coordinator last week, so I can remember everything. Okay, so the main job of the Q coordinator, actually Brian already covered everything. Thank you. So yeah, I'm gonna talk very briefly. So the main job of Q coordinator is making the observing plan for each night. So yes, tonight QC is actually Christine, so I love her. I love her job. So before QC make a plan, every program, I mean the program candidates to be observed should be the prepared status. So this is the example of the OT, and actually this is my program, 24B season. And so in this program, all of you can see the PI's name, and also you can see the principal support email in here. Actually, this is the context. We call this it as a context scientist. But usually in partner countries, so the first contact scientist is a member of NGO, like Sangcha or Jian. But in this case, I was the contact scientist of my program myself because I was the member of Korean NGO. The PI should enter everything about their program, and also in this case, this is the GMOS long sleep program. So I entered the instrument configuration here, and also PI checked the appropriate exposure time. Accordingly, usually when you submit the proposal. So in this case, I entered the 700 second. And sometimes PI needs the fixed position angle of slit. So in this case, the PI should check the available guide star. So in here, there is only one available guide star in this position angle, but the guide star is really bright, which is really great.
So
So
this is a GMOS long slit observation. So it's basically identical to the in setup to the one that we're taking right now.
yeah, that's right.
And the on-instrument wavefront sensor is a little pick-off sensor. It has a mechanical arm like this. And then the Shack-Hartman array is sitting on that little square region where the bright star is that Antoine just pointed out. And so this is the guide star. This is what's sending signals to our telescope to make slight corrections to our Aldaz and to our secondary mirror. So to keep the image quality as tight as possible and to make sure that we're tracking well with the source. Because we want to keep the source right in the center of the slit. If it starts to drift a little bit or the image quality starts to get worse because of our optics, we lose photons, and we don't like losing photons. Or the right kind of photons, the science ones.
Thanks, Brian. So PI should also check the dither. So we already mentioned the detector, the gap of detector, right? So in this case, I set the slit direction to avoid the detector gap. Also, there is a wavelength dither here too. So after finishing the submission, PI set the phase 2 status as for review like this. Then you can see the color turn to yellow. So after PI set as a for review, and then the program will move on to the first contact scientist, the principal support scientist. The assigned contact scientist will check whether all configurations are appropriate, and if they think this is good, and the first contact scientist set this phase 2 as for activation. Then you can see the color turned red. And then finally, the second additional support scientist, in this case, Julia was my secondary contact scientist. So the secondary contact scientist will check everything before the program set to be prepared. So if there are any issues before this program is set to as prepared, the process may go through several iterations. So after all of this process, if there is no problem, then the additional contact scientist set the program to prepare. Then you can see the color is green. So finally this program is ready to be observed. So Brian, if I sync it, then will Gemini observe my program, okay?
I think at the top it says deactivated.
Okay.
Are you?
Okay, so I think most of you already saw this slide. Actually, I wanted to show the real QPT and real today's plan, but Brian said that is a top secret. So yeah, sorry, sorry for it. Yeah, this is the software for the making Q plan.
I'll just mention why it's top secret tonight is because we have the target of opportunities. So we talked about those today in the how to apply to Gemini session. And so these are observations that are very high priority that were triggered in this case a couple days ago, but still extremely high priority. And so those observations are coming up shortly this evening, and so we can't reveal the identity, even though I kind of already did earlier in the session.
Okay, so this is the software for the making cube plan. Like I call it like QPT. So you can see the weather condition actually. So that the program ID and targets are top secret. So I just captured the plans here. So you can see the weather condition. The observer select appropriate plan from these variants based on the weather condition at the time of observation and follow that plan accordingly. So maybe I can ask Mati. So what do you think the weather conditions are like right now?
Yes, so right now we are in I-285 CC7 conditions.
Thank you. So Mati can follow this IQ85 CC70 plan here. Actually, we have another constraint here, water vapor, but recently actually the water vapor is deeply related with the Genius program. So, but we don't have Genius yet. So that's why we don't have water vapor constraint here. Okay, so usually if there is no specific constraint, the priority is by band. So the band 1 programs have the highest priority, followed by band 2, and then band 3. So let me give you a quick quiz. So between a band 2 program from 25A, which is its final stretch now, and a band 1 program from 25B starting maybe next week. So which one would normally have higher priority? Do you have any idea maybe on chat? No one?
So we break up the year into 2 semesters, right?
Yeah.
And so the interface point between the A and the B semester is coming up this Friday, so it'll be August 1st. And so we'll have what we call persistent band 1 programs, meaning they're still not, we haven't totally completed them yet. And so they we're still allowed to observe them because they're high priority in the next semester. And then we also have the new semester observations that are coming in at that point. And so, and Chung's question is, which one of these two would have the higher priority in a given night? Would it be the ones that are left over from the previous semester, or would it be the ones that that are coming in that are new for this semester?
Yeah, so in the last week, one of my mentors said 25A, but band 2 program has a higher priority because the band 1, usually the band 1 program, also even the previous semester, band 1 program can be rolled over the next semester, but band 2 program usually expire when the program is not observed. So the staff usually trying to complete the previous, like at the end of semester, the staff usually try to finish the band 2 programs. So what I mean is actually, aside from band ranking, there are several other factors that affect scheduling priority. So especially toward the end of the semester, there are times when very few programs are actually available for observation during certain time slots. So we call this thin queue. Actually, I still remember when I was doing my observing training last semester, Brian was my mentor.
I'm sorry.
Hawaii. My great mentor. And the weather was actually fantastic. IQ 70cc 50, but the queue was so thin at the time, then that the only program available for those conditions was actually Band 3 program. And it was our boss's program actually, under Nicholas program.
Mm.
So the condition was really good for Band 3. So the target kept saturating. So we had to keep reducing the exposure time. And I remember Brian complaining like, why are we observing such a bright target with an 8-meter telescope?
Don't tell our boss.
Yeah, it's keep a secret from yeah. So my point is that kind of situation can happen, especially in at the end of the semester. So if your targets are toward the at the end of the semester, that might actually increase the chance they get observed and even better conditions. So maybe that's even something you could strategically plan for when writing your proposal and selecting the targets, maybe aiming the thin queue. I think about the QC and the context scientist, that's all from my side. So if you have any question, don't hesitate to ask.
So there was a question from Sungchul about the variants that are planned for this evening. So you notice that every combination doesn't exist there. So that the Q coordinator has only planned for 9 variants this evening. So Kristen's being lazy.
I,
No, there's a good reason for that, right?
yes. Actually, this screenshot, I was the QC and there is no program like.
Oh, this is okay. This is not Kristen. Okay,
Okay.
all right.
So at that time when I was QC, so there was no program with IQ 20, 60, 70. So I only made the IQ 20, 60, 50. So if there is 60, 70 program, but still we can observe in the 60, 50 condition, right? Yeah.
Yeah, and so I mean, usually an IQ 20, a program that requests IQ 20
Yeah.
is looking at something difficult for us. It's requesting top quintile of the seeing. And so it's very uncommon to see a program that's requesting that good of image quality. And then that's also okay with allowing for some clouds. Usually they want the photometric conditions as well.
But I remember there was one program requiring the IQ 20 and 60, 70,
Mhm.
and that
Yeah.
was the actually Korean program.
Yeah, there was another one from UH as well. It's fun to see those science cases that are a combination of very different observing constraints, and that I mean, no matter how much we plan, there's always some really great idea out there that comes up with it doesn't fit our plans, and so we have to remake the plans all the time.
There is another question from Jian. In the QC plan, here one. Do you have any?
Yeah, so prioritization within within the QCE structure is a very complicated cost analysis that we do, and it's actually reasonably subjective. We have some rules like band 1 is generally prioritized over band 2, or band 2 is generally prioritized over band 3, or a rapid target of opportunity is generally prioritized over essentially almost anything else. But a lot of times we have like planetary transits that occur for Maroon X observations or Igrans 2 observations, where there's very limited windows to observe these transits over the course of a semester. And so it may be that a band 2 program that's not as highly ranked as a band 1 program gets a significant boost in priority simply because the temporal windows available, as you say, like limited visibility, the temporal windows available are not many. We also do really try to as targets begin to get lost, so they get to become earlier and earlier in the evening. We really try to get those sources. So even it's mostly band 1, band 2, unless we have the luxury of going to band 3. But if we have a band 2 observation that is setting and we have a chance to get it, we will probably prioritize it over a band 1 that has plenty of visibility. Another complication is not all of our instruments go on the telescope at once. So we have 5 different instruments right now. And so only 4 go on at a time, including Alapeke is one of them. And so so if your instrument's not on there for a specific time, or the instrument's about to come off, we may prioritize a band 2 or band 3 over a band 1 program where the instrument is not going to come off. The same thing, it's fractal, so the same thing happens. We have 3 grading slots for GMOS, and 2 of them are basically always the same. It's a B480 and an R400 grading, so it basically covers like moderate resolution in the blue and moderate resolution in the red. And then we switch gradings around for our third slot. And so a Q coordinator will try very hard to if we have an observation with a grading that's currently in that we want to take out, we may prioritize that over an observation that's a little bit higher priority by the band system. And so it's very complicated calculus, and it does get to be subjective sometimes, because you could ask yourself the question, do I prioritize a band 1 that scientifically is higher ranked, that is kind of on the cusp of setting, for a band 2 that maybe has only a few temporal windows, and it's just because they have the timing window that they get a prioritization. And so some Q coordinators would say, yes, I would take the band 2 over the band 1. Others would say, no, I think the band 1 gets the higher priority. So it averages out in the end. But because we switch roles every week or so, but it's a lot of it's an art, and the moon comes into it as well, and a variety of other considerations. Like we look at the forecast, and the forecast is, at least for clouds and maybe a little bit for like general trends of image quality, that we kind of can see 2 to 3 days out. It's blurry, but we can kind of see 2 to 3 days out. And so we may kind of plan ahead for that, and maybe prioritize a band 2. Let's say the weather's getting worse, a band 2 that needs really good conditions over a band 1 that can absorb a little bit worse conditions.
Yeah, so sometimes it feels like every QC has their own criteria.
Yeah, we have written rules, and there are some that it's very definitely incorrect. But when you get into the subtleties like that, it's complicated. And for GMT or TMT, if it's built, ELT, a lot of this is going to be it's going to be some combination of classical and Q, but a lot of it's going to be Q. And so these this is very valuable telescope time. It's very valuable on Gemini. And so these decision-making processes, people work so hard to get time on the telescope, and we work so hard to make that time valuable to them, that parsing this out and really having a good hierarchy is extremely important. And we've been trying for 5 years to get a machine to take this over, and it's so complicated. The calculus is so complicated that we haven't been able to achieve that yet.
There is another question about the priority. So I think, Brian, you can answer this question.
Okay, so yeah, so fast turnaround is another part of this, which I didn't even mention in the calculus there. Fast turnaround, so that the question is about 25A band 1 being higher priority than 25 band 2, higher priority than FT, and then higher priority than 25B band 1. So as Inchong mentioned, band 2 actually doesn't roll over. And so any band 2 program and any band 3 program, they will stop at the, so tomorrow night is their last night for any chance.
Right.
Yeah, so that's a hard, we're pretty strict about that. So that it basically stops at that point. And so band ones, they roll over. And so there's extra opportunities for program teams to get those observations. And so actually at this point in the semester, band twos are probably higher priority than band one in a lot of cases, everything else being equal. FT is actually prioritized over almost anything else besides like rapid target of opportunity programs or director's discretionary programs. Fast turnaround is like a kind of boost of 20% in terms of the priority. So we think of band 1 FT as a band 0.8, where a lower number is higher priority. And we think of a band 2 FT as a 1.8. And so it kind of wins out against Hey, yeah. Yes, yeah. Yeah, we read. And so fast turnaround completion rates. So we had those kind of typical band 1, band 2, band 3 completion rates. That is much higher for FT. So FT is like you get your data fast, and it's probably going to be complete. We try our best to complete fast turnaround programs. So I'm going to run into the control room. So I'll leave.
So, okay. What can I talk about? So in the meantime, maybe I can introduce the tools, maybe. Okay. So I think most of you already heard about the target of opportunity observation, the webinar today. So I will briefly introduce it. So target of opportunity TO observation refers to unpredictable astronomical events such as gamma ray bursts, supernovae, or gravitational wave counterparts that require rapid follow observations. Actually, one of the strengths of Gemini is its ability to respond to TO observation. And I think C and Brian already told that the rapid TO and standard TO. Yes, but okay, I will mention again that there are two types of TO and rapid TO and standard TO. So by default, the rapid target of opportunity observation is assigned a 24-hour timing window from the moment it is triggered. So actually, I will go over what timing windows mean in more detail shortly. But the key point here is that once the rapid TO is triggered, every step, including the observer or Q coordinator, to execute it as soon as possible within that 24-hour window. So in this screen, okay. So this is the example of the rapid TO program from, I think most of you are, this one. I think most of you are very familiar with this person. Actually, the Professor Myeong-shin Im is one of the most active people in Korea when it comes to submitting rapid TO proposals. So Unless PI specifies otherwise, rapid TOs are typically allowed under all observing conditions. That is, from poor conditions like IQ any, CC any, to very good condition like IQ 20, CC 50. So this means the observation is associated with every weather variant in QPT. So in other words, that program can be observed regardless of the weather conditions. Of course, the weather should be good enough for guiding though. So because of this, the rapid TO usually receive the highest priority in the observing queue for that night. But in this example, yes, they set the cloud cover constraint here. So maybe we can observe this program in every condition, I think. Another type of target of opportunity observation is standard TO. So while it is not as time critical as the rapid TO, but it shares the same basic mechanism with the rapid TO in that the PI triggers the observation after the events occur. So in most cases, the goal is to carry out the observation within a few days, typically within a week of the trigger. So standard TOs are used for events that still benefit from prompt follow-up, but where a delay of a few days does not significantly affect the scientific return. So this makes them more flexible in scheduling compared to rapid TOs, which usually require execution within 24 hours. And actually, this is the example of a standard TO program searching rapid process nucleosynthesis. So once the standard TO has been triggered, it is handled in the same way as any regular queue program. So its execution is scheduled according to its assigned band. In this case, this program is band 1. Okay. So for example, the band 1 standard TO will be prioritized over band 2 and band 3, of course. And the observation is also matched to the observing conditions specified by the PI. In this case, the PI specified IQ 70, CC 70, so the Q coordinator will schedule it in the IQ 70, CC 70 with observing condition in the plan. If the program requires the good image quality or specific high conditions, it will only be considered for execution when those conditions are met. So this approach is actually different with rapid TO. For your information, when you prepare the TO proposal, just like any other program, TO observation must be included in a proposal and awarded observing time through the normal review process. However, unlike regular Q programs, TO observations remain on hold. So yes, unfortunately, in this program, the events maybe didn't occur. So this is currently, yes, on hold. So, uh, so when such an event is detected externally, then PI is responsible for manually entering the target coordinate here and crucially changing the phase 2 status of the observation from on hold to prepare. So this manual change is what officially triggers the observations. Actually, this is difference between the regular Q program and the TO program. So I mentioned earlier that the secondary context scientist can prepare the regular program, but the TO, the PI can set the phase 2 status as a prepared. So once the observation is marked as prepared, the trigger is complete. For rapid TO programs, this action immediately sends an automated alert to the staff on duty. So based on that, the Q coordinator or observer can respond by scheduling the observation as soon as possible. So in the trigger happens during an active night of observing, the current observer can finish the ongoing observation and then immediately switch to the rapid TO program. So this is how we ensure rapid response even during mid of the observation, which is one of the unique strengths of the Gemini Q system. I think you saw this web page. So actually, this is the TO availability page. So the PI can refer this website and then they can trigger their program. So in this page, the PI can check the instrument availability. So tonight, we can use GMOS and iGreens and Maunakea. And also, you can see the GMOS configuration. So the PI can see the currently installed GMOS configuration. Tonight we have R150 grading and B480 R400. Occasionally, certain programs like critical long trend observations are scheduled with strict timing constraints, meaning they can only be observed on a specific date within a narrow timing window. If such program is scheduled and it overlaps with the timing window of TO request, then the TO may not be feasible during that time. To prevent such an overlapping case, the Q coordinator updates the TO availability page to reflect that those specific time blocks are not available for TO execution. So, is everything okay in the control room? Damika? The control room? Everything okay? Is everything okay?
Yeah, we had some technical questions about the program that I'm supporting.
Oh.
So we were
So-
Matti was looking at some observations, and we're looking at a very bright calibrator source, and it was saturating. And so we had to do some tricks and get lucky in order for it to.
You are the context scientist of that program?
I am, yes.
Oh,
Yeah.
that's
So for
great.
the next 2.5 hours or so, it'll be programs that I'm supporting, all on the same target.
Okay, this is what context scientists do. Okay, so
Usually we're not on call at nighttime, but
you're right.
it's a team effort. Now that we're here, it's a team effort. Of course.
Okay, maybe there is some question from.
Yeah, so there was a question from Tekion about so if I want to do the post-processing by myself, can I get the raw data? And how much is the ratio between who uses the automatically processed data and raw data? Oh, okay. So yeah, so we have a really awesome. I'm gonna.
Oh, yeah, maybe I can stop here.
Here we go. All right. So this is our archive interface. It's pretty simplistic looking. But let's say I wanted to retrieve my data from last year or earlier this year, actually. So I would type in here my program ID. I would search for it. And what would come up is a bunch of observations. And so we have the date of the observations encoded in the file name. So for this program, we have different, what are called observations. We have different steps associated with each observation. So this particular one here would be, so this is my designation for my program. This is the observation that was taken. That could be, in this case, it was a science observation, so a spectral observation. This was step 2 of that observation. So you can actually go on that observing tool that Benchong showed earlier. You can find which observation you're interested in, and you say, okay, I want to download that data. And just to be clear, the observation is taken, and within, depends on the night, but between 5 to 20 seconds, the observation will appear on this archive. So if you're, really impatient, sorry, if it takes 20 seconds, but yeah, no, it's a matter of seconds, and it shows up here. And then you can interface with this anywhere in the world. You can download the data, so you can just select a bunch of data. You can download it here. So just download a frame, and then you can bring it up. It'll be a raw frame. Oops. Share the screen. Okay, so here's my raw image. Okay, so I just grabbed a random image here, so I had actually no idea what I was gonna see. So this is a science image. This is so this is actually the program that I spoke about earlier, but like GMOS Moss earlier in the day. So there was 2 programs I spoke about. One was the Go Green program, which was a large and long program by a Canadian team. This was the other program that I spoke about. This is a observation of a high redshift protocluster. So these are galaxies that are associated with this protocluster, and so each one of these slits is trained on one of those galaxies. And so this is something like 40 to 50 objects where each one is on a galaxy, a candidate galaxy, a member of the system. And so you can see the raw data RMS. You see all the cosmic rays, you see the arc lines from the sky, you see 0th order. So these are all 0th orders. So this is the first order, the dispersed spectrum. You can see that there's really bright objects. These are the alignment stars. And so if you're daring, yeah, so in this case, we have reduction packages that we provide. So you do the data reduction, but we provide support for that. So we have the entire data reduction package. In this particular case, it would be an IRAF, unfortunately. But for a lot of the instruments that we use and modes that we use here, we either have Python-based packages that are available from the observatory, or that is done off-site. So, for example, ICRNS 2 is done off-site by an external team. But so for this particular observation, this MOS observation, you would use IRAF and you would reduce the data yourself. You would ingest the arcs, you would ingest the flats, you would ingest the spectrophotometric standard data. You put that all together. And then you would actually reduce the data yourself. You don't have to use our packages. There are Python-based packages that exist outside of Gemini, ones that are open source. So one that's very popular is called Pipet, and it's used for about 50 spectrographs around the world. and now they're starting to develop James Webb Space Telescope spectroscopic capabilities, and PIPET reduces this kind of data as well. So if you're allergic to IRAF, I sort of am, having a Python-based reduction code can be very helpful. Although I don't want to denigrate our IRAF routines too much, because we do have very good READMEs. We have examples, and so even if you don't know the syntax very well, you can kind of follow that along, and it produces very good results in the end. That archive can also be used to grab data from other people. So after 12 months, the proprietary period ends, the normal proprietary period ends. And so you can search any target you want, any instrument you want, and you can see if there are any observations from Gemini, and then you can take those data and reduce them yourself. Eventually, we're going to provide reduced data on the archive itself. This is something that's going to happen over the course of the next couple of years. So it'll be even easier. So you'll have access not only just to the raw data, but to reduced data as well. However, there are many advantages to reducing it yourself. It's really important to understand, like, when we do automatic reduction, sometimes the calibration association is not great. Sometimes, maybe you want to clip out bad data, and the algorithms that we use don't necessarily clip out that data in a way that's optimal. And so I would always advocate, you can do like a quick look based on data reduction that's provided for you, but I would always advocate to dig down into the data reduction packages yourself and really spend some time on reducing and being familiar with your own data, because that can be the difference between not seeing anything and getting a signal. Okay, so I wonder, we have about 20 minutes left, if there are other questions, Sangchul, that we could answer, or other things that we could help kind of set the stage for the summer school that might be helpful.
So far so good. And then I think you guys covers pretty much everything. And then
we could keep going all night, I promise you.
And then it's good to see
In theory.
the weather is weather is great tonight, right?
It's actually not great, and it's still Maunakea. I mean, for any other observing site in the world besides a few others in Chile, this would be exceptional conditions. For Maunakea, it's okay.
Okay. Yeah. And then the audience students, they put already several questions, and then maybe if they have more questions later on, maybe after they go through the your PPT about the Gemini capability, maybe they come up with some questions later on. Then maybe we can also collect their questions, and then later we can send it to you to answer those questions in this document, I think.
Yeah,
So,
we would be very happy to do that. Yeah.
Yes, as of right now, I don't think there's more questions from the audience, I think. I don't know.
I don't see any more in the document right now.
Okay. All right.
So maybe I can just take us back to our observing for the last 10 minutes. We could talk about what the plan is for the night. We could take a look a little bit at the telescope infrastructure, and show kind of how we make the movements in between instruments, and then what's coming next. So
Awesome. Very nice. Go ahead.
So yeah, so this is the view still of Mauna Kea. Hilo is right down here, by the way.
Wow.
And it's not, so actually we can see Maunakea tonight from Hilo, which is kind of a luxury for us. We don't get to see that every night.
I can see the Milky Way.
Yes, and
Milky Way.
and you can see where Keck is looking too. So Keck one
Ah.
is I guess Keck one is lasing right
Nice.
now, and they're lasing at the Galactic Center. It's like
Awesome.
yeah. So this is one thing that we didn't really cover was adaptive optics. We covered it a little bit earlier today, but it's something that I would just encourage students, don't be scared by adaptive optics. A lot of the capabilities, like the really wonderful capabilities of the extremely large telescopes and the 8 to 10 meter class telescopes, those come from adaptive optics. Adaptive optics currently is only technologically feasible in the near infrared, but optical adaptive optics is coming soon. And it seems scary, but it is not. And the technology is amazing, and it's unbelievable that we can do it. But actually setting up these observations and utilizing the power of adaptive optics is not difficult. And so if you want to do precursor science for GMT, using adaptive optics on a facility like Gemini is where you're going to get GMT kind of science, because we are able to shrink the point spread function. You know, IQ 20, where is that? IQ 20 is 0.6 or better, 0.5 microns. For near infrared, it's about 0.4, 0.4 or 0.45 or 0.4. Okay, so that's good. I mean, 0.4 arc seconds is a very tight PSF, but James Webb is 0.1, right? Hubble is 0.1 or 0.15. And so if you want to compete with or you want to synergize well with the space-based telescopes, you need to do better than what the natural ground seeing can give you. And so imposing adaptive optics on an observation drops the point spread function in the best cases all the way down here, so to about 0.1, about the diffraction limit of the telescope. And so we also have what's called a super seeing mode at Gemini, which is called, the technical name is LGS plus P1. We use our first peripheral wavefront sensor, where we made adaptive optic correction off axis. We can do this with NGS. I mentioned this in our session earlier today, and this improves the natural seeing by a factor of 2 to 3. So if your seeing was like, let's say 0.5 in the near infrared, you can get that all the way down to about 0.2, 0.25, something like that. And this can be done almost anywhere on the sky. So our peripheral wavefront sensor, it has about a 3 arc minute probe field of view. So so you just pick a bright star that's, you know, can be far away from your science target, and you can make adaptive optics corrections based off of the wavefront measured at P1. The Shack-Hartman array for P1 is much smaller than for Altair, our adaptive optics system, and so the corrections aren't as good, and they're made non-locally, so that changes things. But don't be afraid to use adaptive optics for your proposals, for your science cases. Dream big; it's really important. So okay, so let's see what we have here. Okay, so just going over the telescope dynamics a little bit. So this is the telescope status display. This is one of Matty's screens that I'm shadowing right now. And this is a schematic view, a top view of our dome and our shutter. So the shutter's open. That's where the telescope is pointed here. And this is a side view of our telescope, of the optical path of the light coming into the telescope. So this is the primary mirror down here. This is the secondary mirror up here. And then it goes down into our instrument support structure or cast cage. This is our tertiary mirror or science fold. And the light is being piped into GMOS right now. And so as Matty takes observations for this the source that he's looking at right now, the light will come from the astronomical object to start off with. And as we saw with the other observations, after a few scientific observations, a set of calibrations will be taken. This is the GCal environment over here. This is our second port on our Cassegrain gauge. And so this tertiary mirror will actually flip around and it'll pipe light from our Gemini calibration environment to GMOS. And we'll take a flat frame, an arc frame, and then it'll flip back and we'll be back on the astronomical source. And so we can do that. We do that without guiding. And then we reestablish guiding once we flip the tertiary mirror back, and then we start taking the observation. This process is very fast. The tertiary mirror is very agile. This is part of one of Gemini's strengths that we mentioned earlier today. This moving between GCal and GMOS is a matter of tens of seconds anyways. And so if you noticed, you'll see some familiar names here as well. You'll see Igrans 2. And then down here is Visitor, but that's actually Maroon X. So that's the other instrument that's on right now. Genius, which is an instrument that we covered earlier today. That's sitting to the side of the telescope. We're fixing it up right now. And that will go on one of these ports at probably within the next month or so. And so if we wanted to switch between like GMOS, so there'll be, Matty, are there Igrans 2 observations this evening or Maroon X, or is it mostly GMOS?
We are definitely filled with news, but there is some Maroon X and Igrans observations as well.
So we're pretty GMOS heavy, but there are a few.
Sorry?
We're pretty GMOS heavy, but there are a few. Is that what you said?
Yes, exactly.
Yeah. So so we actually don't have to do anything physical to switch the instruments. So a lot of telescopes actually have to do entire blocks of, like half the night is this instrument, half the night is this other instrument, or they just do, a certain set of nights. Is the Canada-France-Hawaii telescope does 3 or 4 nights in a row, one instrument, and then they move to another instrument, and they actually have to physically move these instruments on and off. And so we can just, in matters tens of seconds, flip over to another instrument, acquire on that instrument, and take science data. So that movement is faster than our slew speed. And our slew speed is actually quite fast for how big this telescope is. So we can move really, really quick. And so that's one of the big advantages. So we'll be using tonight, it's very common for us to use all 3 of the main instruments that are on. And then this Alopeke instrument is actually sitting in our GCal environment. It has a little pick-off mirror that just kind of comes up in the GCal environment, sticks its head up, and then it picks off and takes the light and does the spectral imaging. And so we have four instruments on tonight. And then so you see in port 4 over here, adaptive optics, and we have another mirror that's in there called the AO fold, which is a deformable mirror. And so this is used primarily for Genius observations, although in theory it could be used for Igrans too as well. So yeah, so I think, so Matty, what does the rest of the night look like? So you're on GMOS right now. I guess you're staying on the same target probably for another couple hours if things look good. I want to interrupt you guys if you're busy there. But it looks like, so just looking at the seeing here, this is again a live view over the last 15 minutes of the conditions. The seeing has stayed relatively steady in a territory that's kind of borderline for us. And so hopefully things will continue to stay flat or even improve a little bit. And we'll continue to take these observations for a couple hours. If it so happens that conditions worsen, or even if they improve, we will stay on this observation. But if they worsen, then it would Matty would at some point switch over to a different plan and take a different set of observations. So we always have something to do. We always have programs that can get useful science out of the conditions that are available. So I think we could leave it there unless there are any last minute questions. So yeah, keep in mind we're available over email, and we are going to meet up with y'all back again in September.
Brian,
And
can I interrupt?
yeah,
If you can VNC to LD1,
Yep.
you can see
Is there, yeah.
you can see some lovely images of a visitor.
Okay. Which screen are you guys on? Because I'll have to scroll through.
5.
It's 5. Yeah.
It's 5.
Almost there.
Yeah, now slide all the way over. Yeah, there you go.
So what are we seeing here, Charlie and Matty? What's your
Beautiful.
professional opinion of what we're seeing here?
So I don't think it's aliens.
Okay.
I think it's
All right.
aliens,
Okay.
but it's moving very fast.
Oh,
Yeah, but this is our 3i.
I see.
This is Atlas.
So these are a couple of acquisition images that you took, and it looks like what was the difference in time between the two images?
Less than, I think, a minute or so. I just wanted to make sure it was the target. It definitely is.
Yeah. So last I heard, and this was a while ago, but it was moving like an arc second and a half per minute. Do you have a good feeling of?
Looks like it. Yeah.
Yeah, something like that. Yeah. So we're in non-sidereal tracking mode right now, right? So we're not following the movement of the stars or the Earth, I guess, but rather we're tracking an object which is moving against the backdrop of the stars. Maybe a visiting object.
Not
Yes.
aliens.
So I think we'll be looking at this. I hope we'll be looking at this for a while this evening.
Ryan, actually, I expect this question, but no one asked about the teal. So,
Yeah, please.
yeah, what happened to the program if the astronomical event doesn't occur in the semester?
Mhm.
I expect this question, but no one asked.
Okay. Yeah. So so programs, as we mentioned earlier today, and I think you covered this as well, programs are set up so with the kind of expectation that there will be an event. So for example, for an interstellar visitor, there was 2 prior to 3i Atlas. And so you could set up a program if you were an ambitious principal investigator saying, well, when the 3rd one comes, I'm going to be ready. And so you could propose to the time allocation committee and say, could I please have an hour and a half on Gemini, north or south, because who knows where it's going to show up. Although probably near the ecliptic. Could I have this time in case something happens to show up? And then you wait, and 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 you get to July 31st, and no interstellar visitor comes, and aw. And so then you say again to the time allocation committee, hey guys, I have a really good idea. I just lost my time because it sunset, the program sunset. It's done at the end of the semester. That's even if it's band 1, it doesn't roll over. Yeah, for targeted opportunity programs, it doesn't roll over. And so, hey guys, I got this really good idea. Remember those other 2 things that came in? There's gonna be a 3rd one. Can you please give me time? We're not. Yeah, okay, fine. And so you just keep convincing people, and that's exactly what happened with this particular program. So a 3i program that I have been supporting for 5 semesters existed, and for 4 semesters nothing happened, and nothing happened, and nothing happened, and nothing happened. And it got to the point where well, we were setting it up and we were doing a good job setting it up in the templates, but I was always thinking, this one again, I have to set it up again, nothing's coming. And then all of a sudden it came. And so then we were well prepared for it. And within a matter of 24 hours from the initial discovery, we were already setting up the observations for the first imaging from Gemini North, and this was a press release that happened recently from the Lab that Jen Miller was a huge part of. That's one of our SOSs here, taking multiband imaging. I think Matty, were you involved in that as well? Making the image, or was it mostly Jen?
No, it was struggling, but it's the raw data.
Yeah. It was a cool image. I liked it. Yeah, so that's what happens. So it could be persistence pays. I mean these are astrophysical timescales, not human timescales, right? So I mean we divide it into 6 Earth months, but you know whatever. Like things take a while, and good things take time. So it you know, one of the things that's going to happen with Rubin coming online now, it's in the south, but it sees a decent portion of the northern sky, is they're going to see a lot more. They're going to see a ton more. They don't, you know, have the limitations that we currently do, and so they're going to be scanning the entire sky every 3 nights. They're going to see a lot more visitors. They're going to see a lot more things go bump in the night, and so we're going to start getting a lot more interrupts. So I think it's not going to be a question of our program's going to not have enough things to look at now. It's going to be, do they have enough time to look at all the, they're going to have to start parsing out what's really interesting and what may not be as interesting. So that's a very, very exciting time. We have 2 telescopes. Gemini is like very prime set up for doing follow-up from Rubin. And so there's a lot of activity here with the staff getting ready for how we might deal with the onslaught of, you know, just all this really cool data that's going to come, and all these really neat phenomena that are going to occur that people are going to want more information on. So I think that's a great way to end it. Yeah, thank you for the question.
Actually, the TO observation is one of the big concern to the NGOs. So yeah, if the astronomical event doesn't occur, then that proposal's time is actually just, it feels like wasting.
Yeah, I mean, you take a chance, right? Because it's like, I mean, especially if you're looking for really spectacular events, really rare events. I mean, it's worth it. It's worth it having a program sitting there at the ready for, you know, I mean, that program was the first to get data on an 8-meter class telescope in the world. They beat out VLT by a night. And so I mean, it does pay off when it happens, but of course you're taking a risk. So it's it can be high risk, high reward. But when it works, it works.
Well, thank you so much, first, Matt, Charlie, for allowing us to shadow you. It's always wonderful to be right here with you in the control room. And Chung, Brian, you were absolutely amazing science hosts. It was a pleasure to be able to host this very first session with the Gemini Korean summer school participants. I do hope we have the opportunity to do so again in the future.
Thank you so much, Jamika. And thank you, Sungchol, Jian,
Thank you.
for setting this up.
Thank
And
you so
for all the
much.
participants. And we'll see you guys again in September.
All right. Thank you.
Okay. Aloha.
Aloha.
Awesome.
Yay.
Okay.